Good morning, guys. Today we're going to work with properties of logarithms, kind of explore different aspects of logarithms that will help us be able to work with them a little bit better. Here you can see we've got three properties, or a lot more that we'll discuss, but we'll just start here. First one's the product property. Now, if you will keep in mind what a logarithm is, a logarithm equals an exponent. So if you think about what's going on with exponents when we're multiplying like bases, what are we doing with those exponents? We're adding them together. If we're dividing like bases, what are we doing with the exponents? We're subtracting. If we are raising a power to a power, what are we doing with those exponents? We're multiplying those together. So these kind of fit along those same rules because they stem from those ideas that we get from exponents, because a logarithm equals an exponent. So if I have log base b of u times v, log of a product, I can say that is the sum of the individual logs. And that's what we have right here. Well, let me give you a quick example. Say I have log base 2 of 4 times 2. Well, we know that 4 times 2 is 8, and we all know that how many times do I multiply 2 by itself to get 8? 2 to what power equals 8? 3. Easy enough, right? Well, if we look at it using this log property, where we separate and do log base 2 of 4 plus log base 2 of 2, well, how many times do we multiply 2 by itself to get 4? 2 times 2, so we multiply it twice. 2 raised to what power equals 2? That's just 1. 2 plus 1 equals 3. So while this obviously would be trivial because we know how to evaluate that left-hand side, I'm just trying to show you how we could break up something maybe a little more complex that we're not familiar with how to work with. And the properties still give us equivalent statements. They still hold true right there. Well, let's look at the quotient property. Quotient property says if I have log of a quotient, then I can just treat that as the difference of the two logs. The log of the numerator minus log of the denominator. So let's kind of keep our example up here. And we'll make that 4 divided by 2. Well, we all know that 4 divided by 2 is 2. Log base 2 of 2 should equal 1 because 2 to the first power equals 2. Well, let's look at what's going on in the quotient property that also allows this to be true. So if I treat it as log base 2 of 4 minus log base 2 of 2, log of the numerator minus log of the denominator, then we should see that that's going to be 2, right? Log base 2 of 4 is 2. Minus log base 2 of 2 is 1. 2 minus 1 equals 1. So that just kind of verifies for us that property. It's an example of that property being true. So it just shows us two ways to be able to work the same type of problem. And in a minute you'll see why we want to use this instead of that, because we won't be able to do that. And then let's go to the power property. Power property says if I have log of a number to a power, that's the same thing as that power times that log. So an exponent to an exponent is just the product of the exponents, as we saw before with just our regular exponent properties. So kind of look at how that might be presented. Log base 2 of 2 to the third power. Well, we know that that's log base 2 of 8, which is obviously going to be 3 because we just multiplied 2 to the third power to get 8. So if we're working over here, if we want to use that property, I can look at it as 3 times log base 2 of 2. The exponent times the log of the base. So 3 times 1 equals, log base 2 of 2 is 1. 3 times 1 equals 3. So just kind of some examples of how that just show how these actually work with some actual values and numbers in them. So that's our three big ones: product property, quotient property, and power property. I've got a few more, we'll call them minor, but they are very important, especially as we get into solving these logarithmic equations later on. But give me a second, I'll get these other few properties up there for us to discuss. Okay, here we have a few more properties that I want to discuss. First we have the identity properties, which they should be pretty obvious. Excuse me. Log base b of b is going to be equal to 1. So anytime the base and the log value are equivalent, you're going to be equal to 1 because b to the first equals b. Common sense kind of thing there. And log base b of 1 equals 0. So it really doesn't matter what the base is, log of 1 equals 0 because 0 is always going to be the exponent that produces a product of 1 right there. So those two right there, again, trivial, but just important for us, seemingly trivial, but important for us to point out. These inverse properties are very, very important because these are what allow us to be able to solve logarithmic equations and inequalities, which is coming up next. So very, very important things. The first one seems should be pretty intuitive. Log base b of b to the x should equal x because we're asking the question, b raised to what power gives us b to the x? Well, obviously to the x power. It also goes back to a combination of our product or our power property, where I can say it's x times log base b of b, which was 1, so which would also give me x. Very, very important concept right there for being able to solve exponential equations. This is a very important concept to use to be able to solve logarithmic equations. A little less intuitive, but we'll look at it here in a second to see if we can try to get you to understand where this comes from. But it says b raised to the log base b of x will equal x. And that just goes back to, if I have log base b of x, it has to equal log base b of x, correct? Well, if I was going to change from exponent form to logarithmic form, logarithmic form to exponent form, I start with my base and I work around the equal sign, right? So b raised to this whole side, log base b of x, has to equal our log value, which is x. So that's where it comes from. Just working with your definitions of exponents and logs and being able to kind of move from one form to the other. Again, seemingly trivial at the moment, but very, very important concept that we need to have down to be able to solve logarithmic equations, which we have coming up very shortly. Another very, very nice problem is the change of base formula we have down here. And what it says is, if I don't like this base right here, I can make it whatever I want. Maybe I want it to be an e. Maybe I want to work with natural logs. Maybe I want it to be base 10, so I can maybe punch these into the calculator. Maybe I just want to make it a nicer base that they both have in common so that I can evaluate. But what it says is, if I have a base I don't like, I can change it by setting it up as log with my new base of my log value divided by log with my new base of the old base. So this base is no longer a base, it's now a log value. So log base b of a is log base, the new base of a, divided by log base, the new base of b. Let's take a step back and look at a problem we looked at in the last lecture where we wanted to evaluate log base 8 of 16. And I said we could use this technique where we set it equal to x, convert it into exponent form, 8 to the x equals 16, change the base to what we want to work with, which they're both base 2. So 2 to the third to the x, and 2 to the fourth. So I get 3x equals 4, right? Bases were the same, so the exponents have to be equal. So then we divide it by 3. We get x equals 4/3. Change of base formula works like this. Say I had my log base 8 of 16 here, and instead of doing all that, what if I wanted to make it log base 8 of 16 into base 2's? Because we know they are both base 2's. So I can go through, and instead of all this mess, I can say, well, what if I make it log base 2 of 16 divided by log base 2 of 8? Log of the log value divided by log of the base. So log base 2 of 16 divided by log base 2 of 8. 2 to what power equals 16? 4. 2 to what power equals 8? 3. So there's the same 4/3 using the change of base formula. And that's where the change of base formula comes from. Think of it kind of like the quadratic formula, where we went through all these steps of completing the square and then we got to this big, beautiful equation of the quadratic formula by doing it in a generic form. We'll just think of it by, like we did right here, setting it equal to x, converting it into exponent form, answering our question with the new base that we happen to want, and then it comes out into that nice, neat and clean formula. We've kind of gone through all the steps. We've asked the questions and asked the questions, and it sticks us right there at the answer. So change of base form is a very, very handy formula. Make sure you get the order right. Very common mistake. People will flip those. I just like to think log of the top number divided by log of the bottom number. But however you remember it, make sure you do, because this is a very handy formula. Give me a second. I'll get a couple examples up here of us using all these different properties. Okay guys, so we have a few examples here of some multiple logs, combining multiple logs by addition and subtraction, even multiplying them by a value. So we're going to use those log properties that we just discussed to try to condense these down, simplify them down to be a single log with a coefficient of 1. So I'll kind of walk through the first one, and I'll let you take a crack at the next three. So if we look at this one, we want to combine these. We notice that they have the same base. So we recognize that when I am adding logs of like bases, then that's just our product property. So I can say that is log base 3 of the product of those two log values, which is 13 times 4. Just like before when we looked at the 4 times 2 as log of 4 plus log of 2, log of 13 plus log of 4 is log of 13 times 4. Clean it up from there. Log base 3 of whatever 13 times 4 is, which is going to be 4052. And that's it. We have combined that expression to a single log. Pause the video, take a few minutes, try to get these next three condensed down to single logs, and I'll wait right here. Okay, hopefully you were able to get the solutions. Let's check your work, see how you did. So on this one we see that we are subtracting the two logs, so that's going to be our quotient property. So I have log base 5 of the first number divided by the second number. So it's the positive log divided by the second, or the negative log. So then you reduce your fraction, log base 5 of 1/2. Yep. Looking at the third one, we have a number times a log, so we recognize that as our power property, so that is the exponent, so it's log base 6 of 4 to the third power, which is just log base 6 of 64. Okay, so we've condensed that to a single log with a coefficient of 1. And the last one's got multiple pieces to it. Just think like you normally do, order of operations. Okay, so we're going to get rid of our exponents first. So move your exponent on up there. So that's log base 4 of 2 to the third power minus log base 4 of 6. So log base 4 of 8 equals, minus log base 4 of 6. Then you do your multiplication, division in whatever order they appear. We have a division right here. So that's log base 4 of 8 divided by 6, which is equal to, when we reduce it, 4 thirds. 4 thirds. Now this is actually a very interesting one we have here, log base 4 of 4 thirds, and it kind of goes back to something that we talked about in the very, very first lecture where we talked about logarithms, and that's evaluating when we can't evaluate. And it's kind of like we do with square roots. 5 square root of 12, it's not a perfect square, or 12 is not a perfect square, so I square root what I can. So we say, well, 4 is a perfect square factor, we'll square root that when we stuck with that square root of 3. Well, we notice that there is a factor of the log value that matches that base. So we could do some evaluating there and try to simplify a little bit. So give me a second. That's what our next few examples are going to work around. Trying to use these log properties to simplify the pieces of a logarithm that I can while being left with the portion that I can't, similar to what we do with simplifying radicals. So here we have a few logarithms that we can't evaluate. We know we can't evaluate them because 5, there are no, 10's not a power of 5, 54 is not a power of 3, 48 is not a power of 8, 1/2 or 6 is not a power of 1/2. So we can't just evaluate even with change of base formula, so to speak, and get rational answers. We're going to have some kind of logarithm left over. But we want to use our properties to evaluate what we can, to get out of it what we can. So let's use those and try to break out the powers of 5 or 3 or 1/2 or 8 that are actually in there and get them out. So if I looked at this first one right here, log base 5 of 10, I can think of that 10 as the product of 5 and 2. So there's a power of 5 that's in there. So we can use our product property that says it's log base 5 of 5 plus log base 5 of 2. Well, log base 5 of 5 I can work out, which is 1. And then log base 5 of 2 I'm stuck with because 2 is again not a power of 5. So we've simplified it to some degree. I say simplified, we've rewritten it in a different manner to evaluate and get the smallest possible log value that we could right there. I don't know that it's any cleaner, but it is a chance for us to get to work with those properties a little bit. Take a moment, pause the lecture, and I'll wait right here while you guys attempt to see what you can come up with for simpler versions of those next 3 examples. Okay, hopefully you were able to do some work with these. Let's see what you got and see how it compares to what I come up with. So log base 3 of 54. So let's see what powers of 3 we've got hidden in there. Well, we can say 54. We know lots of things for 54. Hopefully you recognized it's 27 times 2. If not, you could have recognized 9 and 6, and we could go from there. But if we recognize 27 and 2, that's log base 3 of 27 plus log base 3 of 2. And we know that 3 raised to the 3rd power, so we answered the question, 3 raised to what power gives us 27, plus log base 3 of 2. Not much we can do with that, so it's very similar to the one we had before there. You could look at it, again, there's a lot of ways we could look at these. I could look at 27 as 3 to the 3rd, and then use my product power, or my power property to bring the 3 down, and then be left with the 1. But no matter how you evaluate the log base 3 of 27, you're going to end up with 3 for that. So you should get something very similar to that. And I say similar because there are actually manipulations you could do to get realistically infinitely many, because change of base formula allows us to make the base whatever we want it to be. We have infinitely many expressions that are equivalent to this, but it should be something very similar to that form. Let's look at this next example right here. Log base 1/2 of 6. A couple of different things we can do right here, but I like to start out by, realistically, it's your choice at this point. You could do a change of base to get 2 bases that are easy to work with. So we can go that route right there and say that I can work base 2 off of this, and I can work base 2 off of this. So I can look at it as log base 2 of 6 over log base 2 of 1/2. If you're really not comfortable with that 1/2 base, we can change it to something neater and cleaner. So the denominator is just going to be -1, right? 2 to what power is the reciprocal of 2? -1. Numerator is log base 2 of 2 times 3. Product property tells me that's log base 2 of 2 plus log base 2 of 3, all still over -1. So we're going to end up with log base 2 of 2 is 1 plus log base 2 of 3. All over -1 is -1 minus log base 2 of 3. So that is a little bit cleaner version of that expression right there, because we may have some other things that we could do with that -1 right there. Let's look at this one if we'd have gone the other route with it. We won't get the exact same thing, but we will get an equivalent expression. If we'd have just done what we did on the first problem, first two problems, and just say, well, I know that 1/2 has a, or 2 is a power of 1/2. I could make it log base 1/2 of 2 times 3 and get log base 1/2 of 2 plus log base 1/2 of 3, and that's going to give me -1, right? 1/2 to become a 2 needs to be reciprocal, so -1 plus log base 1/2 of 3. So that one's just as clean as the other one we had, the -1 minus log base 2 of 3. So what we should recognize, these two are equivalent expressions. So it's very interesting and neat how that is true. So you may want to just kind of play around with those two and look at what relationships or what properties of logs are making them equivalent just by swapping that sign and inverting the base, because we haven't looked at any properties that mess with the base other than change of base formula. So it's again, interesting thing to look at, but you could get both of those. As I said, infinitely many solutions that you can get when you're simplifying these based on whatever you are comfortable making your base. All right, let's look at number 4 here. Number 4 kind of works with that same idea that it's personal preference on what we decide we want that base to be. So if you want to make it base 2, which is not a bad option right off the bat, because there's nothing that jumps out at me unless you want to say that 48 is 8 times 6. Not a bad, go right there. So we could have log base 8 of 8 plus log base 8 of 6. Well, that's going to give us 1. No big deal there. The 8, the log base 8 of 6, again, we know we need to work with powers of 2 there. So that's log base 8 of 2 times 3. So that'd be log base 8 of 2 plus log base 8 of 3. And we can change the base formula of this to figure out, it should be 1/3. I know that because of, I understand, I know about rational exponents. So if you've worked with rational exponents before, 8 to the 1/3 power is 2. But if you don't recognize that, change a base formula, base 2, 2, base 2, 8, will quickly make that obvious to us. So log base 2 of 2 is 1, log base 2 of 8 is 3, so there's the 1/3 for log base 8 of 2. And log base 8 of 3. So we end up getting 4/3 plus log base 8 of 3. Okay. Relatively clean little answer right there. Now, we can work it a different way and just go to the base 2 at the very beginning. Yeah, go to the base 2 at the very beginning of the problem. And again, we won't get the same answer, but we'll get an equivalent answer. So if I said log base 2 of 48 over log base 2 of 8, well, we know that denominator is going to be 3. No big deal there. Okay. The numerator, 48 is not a power of 2, so I've got to break it off. And what's that, 16 and 3 is the biggest power of 2 we can get off of that. So that's going to give us log base 2 of 16 plus log base 2 of 3, which there's the piece that we're going to be stuck with, right? Log base 2 of 3. And we get log base 2 of 16 is 4 plus log base 2 of 3 all over 3. And again, going through and trying to clean it up, that's 4/3 plus 1/3 log base 2 of 3. Remember, divide by 3 means times 1/3. And we can use our exponent rule here. which the 4/3 showed back up just like it should have. Your rational stuff will always show up the same. It's the just the version of logarithm that you end up working with. So 4/3 plus log base 2 of 3 to the 1/3, which you can leave it like that if you want to. If you recognize rational exponents, I'll give you a little peek into them. A 1/3 exponent is a cube root, as we saw earlier when we had 8 to the 1/3 equaled 2. Cube root of 8 is 2. So this right here, again, we have equivalent expressions. The 4/3 will match up. That's pretty easy to see. But log base 2 of cube root of 3 and log base 8 of 3 are equivalent. This is, again, this one's a little bit cleaner than that one, but you don't know that at the very beginning unless you recognize, or you don't know because it's just whatever you pick step to go off of. So again, infinitely many answers you could get depending on what base you want to focus on, what the leftover log is going to be, but you can still get a lot of it very, very similar. So not just one answer, but it's more about the process of being able to work fluently with those properties. They come in very, very handy when we get ready to start solving and we need to start digging into our equations, our logarithmic equations. That's it for properties of logarithms, and I will see you in class tomorrow, guys.